I'm going to start at the very beginning. Is what are X-rays? Okay? And X-rays are just light. Right? And so if you think, oh boy, it's going to be really tiny, isn't it? So the visible spectrum, you think of a rainbow going from low energy to high energy, or long wavelength to short wavelength. And, I don't know, I see lots of rainbows here in Ithaca. But if you kept on going down, you get into radio waves and the microwaves and so on. And in the old days, we used to have crystal radio sets. You had to string a wire over the top of your house, because that's the wavelength of the radio wave. If you go the other way, you get up into the ultraviolet and then the X-rays, and then way up here is gamma rays and so on. So some of the stuff which is coming from the sun right now is way up there. So why do we care about X-rays? Well, we've all had dental X-rays, chest X-rays, and things like that. And so the key property of X-rays is they penetrate through things, and they don't hurt. Your sensation when you get a chest X-ray is, did you do it? They're not even a click anymore, right? They just hold still, don't breathe, and it's like, then it's done. So it certainly doesn't hurt. There's no real sensation. They go right through, and most of them go right through you. But it allows us to probe the structure of things on all kinds of length scales. Think of like shipping containers coming off of a container ship, if you're looking for big things in it, or medical X-rays, all the way down to atomic scale dimensions. And so a synchrotron, think of it as a really bright X-ray light bulb. Okay, if you compare the light from a candle to lights at a football stadium, that's about the right ratio for the X-ray machine in your dentist's office and the synchrotron. Okay, so it's a huge difference, right? And then think of all the things you can see here that you can't see here. You can see colors, you can see motion, you can see broad field of view. All of those things apply to the synchrotron as well. So I really like that analogy. Okay, so how does the synchrotron work? We live off the legacy of our particle physics friends that built accelerators. And let's see if I can get this to go. So, and basically it's charges that go around and around in a circle. And if you accelerate a charge, it radiates light, right? And so what happens is the question is, why is he talking about accelerators? Right? That's because this is how we generate the X-rays. So as they go around and around, basically radiation comes off like the headlights on a car. So if you think about a car going around a racetrack and you're just looking at every once in a while the headlights will sweep by, that's what's going on. And we have another trick where we actually put a whole bunch of magnets in here so it wiggles it. So as it goes through these things we call undulators, you get a really bright shot of light coming out, goes through your sample and into the detector. Okay, I'll narrate it. What you're seeing, this is supposed to be an electron going through the particle accelerator in our history of the accelerator complex. Here's the wavelengths going from gamma rays down, and the X-rays are at about the size of an atom. So that's a key thing, is the wavelength of the X-rays about it. So this is where we live, underneath Alumni Field. We're 5 stories underground, and the storage starts, we boil off charges here. They come up through the linear accelerator. There's actually 3 accelerators. A linear accelerator, which goes from 0 to 100 million volts. It then comes around the corner into the synchrotron, which is a circular accelerator. And that will take from the 100 million up to 6 billion electron volts. It goes around and around. And then after it gets up to energy, so we're now about 99.999% of the speed of light, gets transferred into the electron storage ring, where it stays forever. Okay. One curious thing about us is, due to our history of being an electron-positron collider, for reasons that had to do with it was easier and cheaper, we actually still use the positrons. So we have more antimatter in the lab than most places on the planet. So we could stay there for hours. I was talking about the magnets. What they do is these bunches of electrons come through, they wiggle them, they add up, and then so the light, though, comes off tangentially into these, we call them hutches. They're basically little experimental stations. So when all my users come to town, we tell them just treat this as a huge light bulb. They push the button, the shutter opens, X-rays come out.
At one point, I've heard about a famous painting coming into the
Yes.
chest to be analyzed, and I'm just wondering if that sticks out in your memory, or if there were any other like really cool experiments that.
There have been several paintings, and as a security measure, I don't even know when they're coming. So there's been Picasso's and several things. We're really lucky that the Johnson Museum is here. And so they have secure vaults and they know how to do this kind of stuff. And one of my scientists, Louisa, she's actually the one that's running the new biology beamline, is also an art historian and has worked at the Metropolitan Museum on conservation and so on. And is really interested in finding paintings beneath paintings, but we also done things, reading scrolls that are rolled up and then unrolling it digitally, or things where you can't see it anymore with your eye. We can frequently find the remnants of the ink, and that a particular mineral will have a signature, and so on. So there have been many of them, but I never got to see it. We've had some really cool experiments recently where Bruce Van Dover and Mike Thompson are doing an experiment, completely machine-controlled experiment, where they have a wafer which has 3 different elements, A, B, and C, in different concentrations. So different points on the wafer are different stoichiometries. And then they have a laser which anneals it. And then so what they do is they'll anneal it, measure the properties of the stuff they just made with the laser and a couple other optical probes. And then the computer decides what to do next, changes it and moves to the next new composition and so on to materials discovery. And and Carla Gomes is involved in it and so on. And it's really one of the first examples that it's actually not, it works. So that's a little bit like the bomb. It works. That's the secret, that they were able to get it to go without any human, and it actually moved towards a better material, and so on. And so, that took a lot. And so those kind of things are coming on. And I'm really excited to see some of the plant stuff which is going to happen. There will be growth boxes, carbon dioxide light boxes, and so on. This high field magnet. Some of the stuff that the structural materials guys added. There's just been so much. Oh, I forgot to mention, there's 2 Nobel Prizes. Rod McKinnon for the potassium ion channel and Ada Yoneth for the ribosome were both done at CHESS. So, we've got so much to be proud of and exciting. That the best day of the week is Monday. It's not everybody says it, but I get to go, and the experimenter's been running all weekend, and they're all so excited. You walk by and they want to show you their results, right? So I get to walk around, but everybody's happy. The worst day is Wednesday afternoon because they just started and nothing's working. So I don't go out there then. I go on Monday mornings and go talk to the users. But and every week, right? There's another 8 or 10 groups are coming through, and there are so many graduate students and so on. And it's just really fun to be there. That's the fun part. Thanks.